now we get into the nitty-gritty of the life cycle of a star. And you're going to see some of the terms that the Hertzsprung-Russell diagram has on it. You're going to see these terms in the different stages of the life of a star. The first stage that a star arrives at, as it is alive, okay, has what we call nuclear fusion going on in its core. This little figure I've brought in has the hydrogen plus hydrogen going to form helium and releasing a lot of energy. So that's actually the first stage of every star, whether it's a low mass star or a high mass star. The main sequence is the first stage, and the speed at which a star that burns through this cycle, or should I say the length of time the star is on this cycle, depends upon the mass of the star. So for instance, something that is 10 times the mass of our sun actually will only be doing this for about 20 million with an M years. That seems like a long time. Our sun, which is like what we call one solar mass, our sun actually is going to be a main sequence star for 10 billion years. And at the end of this slide, I'm going to say it's been about, we said 4.6 billion years ago was when our sun turned on. So if you round that to 5 billion years, so that's why we say our sun is about halfway through our 10 billion, with a B, years of being a main sequence star. That's significant. Now, low mass stars actually they just do things a little bit more slowly. They have less mass to start out with, but they burn through that mass slower. So for instance, if you had a star that was about half of the size of mass of our sun, it would actually be a main sequence star. It would stay in that cycle for not 10, but 80 to 100 billion years. Now that sounds like a long time. So, like I said, currently our sun is in its main sequence cycle. It's about halfway through. It's got about half to go. Now, we're going to be talking a little bit more about what happens to stars when they're done with this stage of their life. But what's going to be with our star, our sun, is it's going to become a giant, and it's going to blow it out. It's going to expand actually beyond the orbits of Mercury and Venus. Sad face, right? So stars that begin nuclear fusion in the core, we say they become alive and they become main sequence stars. Now, as they run out of hydrogen to fuse into helium, basically they build up helium, and what they do next as they become no longer main sequence stars depends upon their mass of the original star. Low mass stars, I'll just leave it that way, they basically don't do anything else. They just become a brick of what? Helium. Stars between 0.4 times the mass of our sun and 8 times the mass of our sun, so this would include us. What they do is actually, we say on the HR diagram, they move up, or they leave the main sequence and become giants. And thus our sun actually will begin fusing heavier elements, like it'll take helium and fuse it together to make, is it carbon? So it will begin a next step of nuclear fusion in its core, but it won't last near as long. That stage won't last near as long as the stage it was the main sequence. So it'll move up and become a giant. You saw in the HR diagram kind of where those were, kind of up and over to the right a little bit, and then it will cool off, and it will eject its material and give us a planetary nebula, and then it will kind of cool off and become a retired star, a white dwarf. So something that's more massive than 8 times the mass of our sun, and I'll go ahead and say 8 to 25 solar masses, it actually will not end its life quietly, like with the giant planetary nebula, white dwarf. It will blow up. Just the physics of it, it will blow up. And if it's up to 25 solar masses, as it was a main sequence star, then it's going to blow up and give us a neutron star. And I have a slide coming up to what is a neutron star. That is so cool. It's there's another type of retired star. You know, we have white dwarf retired star, neutron star retired star. Well, if it's more than 25 times the mass of our sun, the physics are that it basically, as it ends its life, it will blow up, but the remnant that's left behind will not be a neutron star, but instead the little object left behind will be a tear in the fabric of space and time we call a black hole. Is that not cool or what? That's one type of, actually two supernovas. Those are both, these supernovas are the same. But if it's really massive, then we get a black hole. Not so massive, we get a neutron star. So let me look at my notes here. Yeah, so here we have a diagram to kind of show you how this works. Here's the HR diagram, and we're starting with just here low mass stars. So notice here, this could be our sun, right? Okay, it's a nice yellow star, kind of midway on the main sequence stars on an HR diagram. Okay, so this stuff right here, don't let it throw you off. This actually was stuff we talked about a little bit earlier. We said that our sun, because of the associated with condensation theory of the formation of our sun and the planets, it was a proto-sun, and before that it was just a nebula. But focus here now on, in 5 billion years, okay, it's actually going to run out of hydrogen to fuse, and it's going to leave the main sequence and become a giant. It's actually going to go ahead and fuse helium to make carbon and become a variable star, but at some point it's going to kind of give up the ghost, no longer have nuclear fusion going on, and it's going to, some of its material is going to be ejected into what we call a planetary nebula. The little core of what used to be a star, our sun, will cool down and become a white dwarf. So that's a low mass star. Planetary nebulas, then, if you're out at the observatory, sometimes they'll say, oh, that's a planetary nebula. So hopefully we're kind of on the same page here, that planetary nebula are just kind of, there's like a retired star in there, and it's kind of sloughing off its material, and it forms these various shapes. And these various shapes actually, then we go ahead and name it, the nebula, for what its shape looks like. So this is a beautiful Eskimo, it's called the Eskimo Nebula, it's a planetary nebula. So high mass stars, stars that are more than 8 times the mass of our sun, are either they're going to blow themselves up in a supernova and end up as either a neutron star or a black hole. So here's a figure to kind of show how that works. Here we have kind of, again, in the beginning, they form from a nebula, and here it's called just an interstellar cloud, the same difference. Protostar, kind of the beginning of the star, high mass star forms. This would be main sequence right here. Main sequence star, okay? Then it leaves the main sequence relatively quickly, and then we get a red supergiant. And at some point then, no, not necessarily long after that, we get a supernova explosion. Well, define long, right? In terms of a star, it's not very long. Supernova, specifically not just any supernova, but both the up to 25 solar masses and beyond, we get a type 2 supernova. What's left then after the explosion is, or what we call a little, I call a little nubbin, the thing that used to kind of be the core of the star. And if it is, what we said, 8 to 25 solar masses, then it becomes a neutron star. And if the star as a main sequence was greater than 25 solar masses, then the thing left over becomes a black hole. So you might be wondering, well, what does that look like in outer space? Well, we've actually got, this is the, I believe, the Crab Nebula. It's called Messier Object 1. And this is a supernova remnant. You can kind of see if it looks like, you know, there was something explosive happening at some point long ago. There was. So just to kind of finish up, I've got some photographs of some different planetary nebula. So again, these are stars that are at the end of their lives. Basically, the gravity is losing hold of the matter that's kind of on the outer edges, and they make these beautiful shapes. There's the Gum Nebula, There's the Butterfly Nebula. And there's the Glowing Pool Nebula. Aren't they beautiful?